Okay, so welcome to this next video in which we are discussing angiogenesis in chronic inflammation. Okay, so we've discussed that in chronic inflammation, the T lymphocytes and the macrophages which are in the interstitial space will be releasing two angiogenic factors known as vascular endothelial growth factor A, VEGFA, and fibroblast growth factor 2, or FGF2. Right, we've then discussed that vascular endothelial growth factor A will work on a receptor which is the vascular endothelial growth factor receptor 2. Now, let me show you the structure of one of these receptors. So basically they have the typical receptor structure for a receptor tyrosine kinase. So they have many in what are known as immunoglobulin-like domains, which is a certain type of domain that is on the extracellular portion of a receptor tyrosine kinase. Okay, so it's just a certain structure in the protein, and I realise now that I haven't got enough space to show the other portions. So let me transfer this picture up here. So these little blobs that I'm drawing, these are supposed to represent the immunoglobulin-like domains, okay? And the vascular endothelial growth factor receptor 2 has 7 of these immunoglobulin-like domains. Okay, so we have 7 immunoglobulin-like domains on the extracellular domain of this receptor tyrosine kinase. So 7 immunoglobulin-like domains, and there should be a little dash between immunoglobulin and like, okay, domains. Right, so then what you have is a transmembrane region which spans the phospholipid bilayer of the endothelial cell. So here's the phospholipid bilayer, so this is the cell membrane of the endothelial cell. Okay, and then the intracellular domain of this receptor tyrosine kinase. What this consists of is 2 halves of what's known as a tyrosine kinase enzyme. So you have a split tyrosine kinase enzyme. So these 2 portions that I've shown here, these are the 2 halves of the receptor tyrosine kinase. So let me show this. This is a split tyrosine kinase domain. Okay, so they need to dimerize in order for the enzyme to actually become active. So split tyrosine kinase domain. Okay, right. Then you have a little portion separating these 2 halves of the tyrosine kinase, basically. And this is a 70 amino acid long piece of polypeptide. So this is 70, and then people put alpha alpha to mean amino acid, and it's known as the kinase insert because it's inserted between the 2 halves of this split tyrosine kinase domain. Okay, so it's the 70 amino acid kinase insert. Alright, so let's highlight up the different portions here. So we'll have the split tyrosine kinase domains in purple here. Okay, then we'll have the 7 immunoglobulin-like domains in turquoise. And I'll just put a few little lines in here to show willing as to colouring those dots in. Okay, and then we've got the transmembrane region, which is quite important, which we'll have in red here. Okay, so what's going to happen basically is that vascular endothelial growth factor A is going to come and bind to this vascular endothelial growth factor receptor 2, and it's going to promote the dimerization of these vascular endothelial growth factor receptor 2s. So let me show this. Okay, so basically vascular endothelial growth factor A is a dimer. Okay, so when we talk about vascular endothelial growth factor A, what we really mean is 2 vascular endothelial growth factor A proteins stuck together. Okay, so this is what we mean by vascular endothelial growth factor A, or VEGFA. Now what will happen is that one vascular endothelial growth factor A will bind to one of the vascular endothelial growth factor receptor 2s, and the other will bind to another, and this will promote the dimerization of the these two separate vascular endothelial growth factor receptor 2s. So let me now show it, and I think because I've shown the two separate components of the vascular endothelial growth factor A as circles, which I'm now highlighting in pink, I will show the immunoglobulin domains as squares. It also is going to save me some effort, because now what I can do is I can just draw a great big rectangle, like so, and then just separate it up into 7. 1, 2, 3, 4, 5, 6, 7. There we go. And then we've got another vascular endothelial growth factor receptor 2 over here. Okay, so here are the immunoglobulin domains. So 1, 2, 3, 4, 5, 6, 7. Okay, and I didn't mean to imply here that it actually binds to the first immunoglobulin domain. It binds much more spaced out than that. Okay, so these are much bigger and bind to far more of the immunoglobulin domains than just the first two. Okay, so don't read too much into that. It's just binding to one here and binding to the other here. Okay, and that's all this picture is supposed to show. And then both of these are inserted in the phospholipid bilayer, like so. And now, once they've dimerized in this way, what's going to happen is their receptor tyrosine kinases are going to become active. Okay, so these originally split receptor tyrosine kinases are going to become active tyrosine kinase enzymes, and they're going to stick phosphate groups onto tyrosine residues. Okay, so let me remind you of the structure of the amino acid tyrosine. Okay, so we'll draw it as an amino acid residue rather than just as the pure amino acid. So here's the amino group as though it's in a polypeptide. So above here would be the carboxylic acid group of the next amino acid in the polypeptide. Here's the alpha carbon with a hydrogen coming off, and here's the carboxylic acid group of this amino acid, and then it will be linked to the amino group of the next amino acid along. Then the R group of tyrosine is, you have a methylene group here, followed by a benzene ring here, which I'll just draw as a hexagon with a circle in the middle. Okay, so that represents a benzene ring, and this benzene ring has an alcohol group coming off it. Okay, so this is the structure of a tyrosine amino acid residue, and the single letter amino acid code for tyrosine is Y. Okay, now what you can do is you can add phosphate groups onto tyrosine residues. So here I'm going to draw a phosphate group. So we have a phosphorus atom, and I think I should move this right into the center. So we have a phosphorus atom, which is double bonded to an oxygen up here, and then single bonded to another oxygen, which has acquired an electron ionically from somewhere, and therefore has a negative charge. And then this phosphorus atom also has two alcohol groups coming off it, so one here, one here. And what can now happen is that you can form what's known as a phosphoester link between the phosphate group and the alcohol group on that tyrosine residue. Okay, so you can take off the hydrogen from the alcohol and take off the whole alcohol from the phosphate, bind those two together to make water, and that's why this reaction would be called a condensation reaction, because it produces water. So this is a condensation reaction. Okay, and then you can bind the oxygen to the phosphorus atom over here, like so. And that link between the alcohol group and the phosphate group is what's known as a phosphoester link, or more correctly a phosphate ester link, but people often use that abbreviation, phosphoester link. Right, so you can add phosphate groups onto tyrosine residues within proteins,